Hey everyone, welcome back. Today we're going to be taking a deep dive into the world of rare earth elements.
Those crucial ingredients for so much of our modern tech.
Exactly. And you know what's really fascinating? Scientists are using some pretty cool techniques to learn even more about them.
Yeah, even when they're working with incomplete data.
Wait, hold on. Incomplete data. What's that all about? Before we get too deep into that, I think we need a little refresher.
Definitely.
What exactly are rare earth elements? And why should we care about them?
Okay, so picture the periodic table.
Like the giant chart of elements from chemistry class.
Exactly, and there's this special group of 17 elements huddled together.
Oh, right. I've heard about those.
They're called rare earth elements.
But aren't they actually, not that rare?
Yeah, you're right. The name is a bit misleading.
So what's the deal with them then?
Well, they're not rare in the sense of being super scarce. It's more that they're spread out really thinly across the Earth's crust.
Oh, I see.
And what makes them so special are their unique electronic and magnetic properties.
Okay, so they're like the secret sauce that makes all our gadgets work.
Yeah, pretty much. Think about the strong magnets in wind turbines or the vibrant colors on your smartphone screen. You can thank rare earth elements for that.
Wow, that's pretty cool. But they're used for more than just gadgets, right?
Absolutely. Scientists use them to understand how our planet works.
Really? Tell me more about that.
Okay, so imagine them like fingerprints left behind by geological processes. By analyzing the amounts of different rare earth elements in rocks, scientists can figure out how those rocks formed, what conditions they were exposed to, and even get clues about the Earth's history.
So it's like having a time machine, but instead of actually traveling through time, we're deciphering the chemical stories locked away in rock.
Exactly. It's pretty amazing what those elements can tell us.
It really is. Okay, so you mentioned incomplete data earlier.
Right.
What's the issue with that? Why is it a problem?
Well, imagine trying to solve a jigsaw puzzle, but with some pieces missing.
Oh, that's frustrating.
It is, and that's kind of what it's like with incomplete data. Older methods for analyzing rare earth elements often resulted in, well, gaps in the data.
Like we only had half the puzzle pieces.
Yeah. And even with modern tech, we sometimes run into limitations or specific lab procedures that lead to missing data points.
So even though these datasets could hold all sorts of valuable clues about Earth formation, mineral deposits, and more, we're missing out on a big chunk of the story because of these data gaps.
Exactly. And that's where this awesome technique we're talking about today comes in.
You mean polynomial modeling?
Yep, that's the one.
Okay, so what in the world is polynomial modeling? Break it down for me.
All right, imagine you're plotting the concentration of each rare earth element on a graph.
Okay, I'm picturing it.
Now, if you've got some data points missing, polynomial modeling uses a mathematical equation to basically draw a smooth curve that fits the existing data. That way, you can predict those missing values.
Oh, so it's like connecting the dots, but with fancy math.
Yeah, it uses the relationships between the known rare earth element concentrations to figure out what the missing ones probably are.
That's really clever. But how do we know if these predictions are any good? I mean, are they actually accurate?
That's a great question, and that's where things get really interesting. They are. It's like giving the model a pop quiz to see how well it performs.
Okay, so did it pass?
It totally did. The predicted values matched up with the actual values really well. Like they were within the typical margin of error you'd expect for this kind of measurement.
So it's not just a cool idea, it actually works.
It really does. And that's exciting because it means we can potentially go back and revisit some of those older studies with incomplete data and see if we can learn even more.
Like opening up hidden chapters in Earth's history book. That's awesome. I'm curious, are there any specific examples where this polynomial modeling has been used in practice?
Absolutely. There are actually quite a few. Let's start with one that focused on ultramafic rocks.
Ultramafic rocks, those sound pretty hardcore.
They are. They come from deep down in the Earth's mantle.
Wow, so we're talking about rocks that formed millions of years ago.
Exactly. And the original data for these rocks, going all the way back to 1971, had some gaps in the rare earth element measurements.
So we're talking about giving new life to old data here.
Yeah, exactly. By using polynomial modeling, researchers were able to fill in those missing values and get a much clearer understanding of the rare earth element patterns in those rocks.
So they were able to learn more about how these rocks formed deep within the Earth all those years ago, just by filling in some missing data points.
Yep. Pretty cool, huh?
It's amazing to think that we could take data collected decades ago and still extract new insights from it.
It really speaks to the power of scientific data. And here's another interesting example, this time with basaltic rocks from Iceland.
Iceland, the land of fire and ice, and volcanoes, right?
Lots of volcanoes. And the original data set from 1979 was also missing some rare earth element values.
Sounds like polynomial modeling came to the rescue again.
It did, and it helped researchers learn even more about these Icelandic rocks. In fact, the more complete picture they got from the filled-in data provided further evidence for something called mantle heterogeneity.
Mantle heterogeneity. That sounds kind of complicated.
It's not that hard to grasp. Basically, it means that the Earth's mantle, that layer beneath the quest, isn't just one big uniform blob.
Oh, okay.
It has different regions with slightly different compositions, kind of like a giant molten marble cake with swirls of different flavors.
Okay, that analogy I get. So these Icelandic rocks, by having their missing data filled in, helped confirm that the mantle is more like a swirly cake than a plain one.
Exactly. And by understanding those swirls, those variations in the mantle, we can learn more about things like plate tectonics, volcanic eruptions, and even the formation of valuable mineral deposits.
Wow, so we've gone from smartphones to ancient rocks to the Earth's mantle, all in one deep dive. This is amazing. Are there any other real-world examples that show how powerful this technique is?
You bet. There's one more I think you'll find especially fascinating. This one involves a type of rock called kyanite-eclogite.
Kyanite-eclogite. Never heard of it. Tell me more.
These are some seriously tough rocks. They form under intense pressure and heat deep within the Earth, often during those massive collisions between tectonic plates.
Like when mountains are formed, continents smashing into each other.
Exactly, major geological drama. And, as you might have guessed, the original data set for these rocks from 1987 also had some missing rare earth element values.
But with polynomial modeling, they were able to complete the data set and learn more about how these rocks form.
You got it. It's like being able to rewind millions of years and watch these epic geological events unfold. So we've seen how this technique can unlock new insights from old data, but what about its applications in modern research? Could it help scientists working with brand new data sets too?
That's a great question. It seems like this technique could be a real game changer for rare earth element research, breathing new life into old data and helping us make sense of complex new data sets. So where do we go from here? What does the future hold for polynomial modeling and rare earth elements?
It definitely could. It's pretty exciting to think about all the possibilities. I mean, we could see a whole wave of scientists going back and re-examining old research, studies that might have hit a roadblock because of those incomplete rare earth element measurements.
Like a renaissance of rare earth element research, all thanks to this new tool.
Exactly. It's like getting a second chance to unlock even more knowledge from data that's already out there. But it's not just about looking back. This technique is really useful for modern research, too.
Right, even with all the amazing technology we have today.
Yeah, even then, sometimes you just can't avoid those gaps in the data. Instruments have limitations, there could be interferences, or sometimes certain lab procedures just make it tricky to measure every single rare earth element.
So even the best scientists sometimes end up with a puzzle with a few pieces missing.
It happens. But the good news is that polynomial modeling gives us a really solid way to fill in those blanks. It means researchers don't have to throw their hands up in frustration when they hit a snag.
They can still get valuable insights from their data, even if it's not perfectly complete.
Absolutely. And remember, we're not just talking about understanding rocks and the Earth's history here. Those rare earth elements are crucial for all sorts of technologies.
Like those smartphones and renewable energy technologies we talked about earlier?
You got it. So if we can get even better at analyzing and interpreting rare earth element data, it could lead to all sorts of advancements in fields like renewable energy, electronics, maybe even medicine. It's like a chain reaction of awesome.
Wow, that's incredible. It's amazing how those tiny elements, those rare earth elements, can have such a huge impact on our world.
They really can. It just goes to show you how everything is connected, from the formation of rocks deep within the Earth billions of years ago to the cutting-edge technologies we rely on today. It's all part of the same story.
And who knows what other pressures are waiting to be written. As scientists develop new tools and techniques, like this polynomial modeling, I bet we'll keep uncovering even more fascinating connections.
I think you're right. It makes you wonder what other secrets are hidden away in those limited data sets we've been talking about.
Yeah. What other mysteries are just waiting to be solved with the right approach? It's pretty mind-blowing when you think about it.
It really is. Makes you realize that even with all we've learned, there's still so much more out there to discover.
Well, that's the beauty of science, right? It's a never-ending journey of exploration and discovery. And that's what makes it so exciting.
Couldn't have said it better myself.
Well, on that note, I think we've reached the end of our deep dive into the world of rare earth elements and polynomial modeling. Thanks for taking this journey with us.
It's been a pleasure. And remember, if you're as fascinated by this stuff as we are, be sure to check out the source material we've linked in the show notes.
There's a whole lot more to learn about these amazing elements and the clever ways scientists are studying them. Until next time, stay curious.